Welcome back to this course on advanced memory hierarchy design. In this lesson I will discuss how virtual to physical memory address translation can be avoided during cache access. This figure shows a conventional cache organization. The CPU generates virtual addresses. The virtual address is then sent to the TLB to obtain the physical address. Then the cache is accessed or indexed using the physical address, and if there is a cache miss, the physical address is sent to memory. Because the cache is accessed using a physical index and because the tag is also part of the physical address, this cache organization is called physically indexed and physically tagged. The problem with this organization is that it increases the level 1 hit time. The L1 cache access is typically on the critical path of the processor, and now we have to do a TLB access and a cache access to obtain the code or data. What can we do about this? First, let's consider this question. Does physically indexed, physically tagged mean that the TLB and the cache always have to be accessed sequentially? Well, let this figure be the division of virtual addresses into page number and page offset. And let this be the division of an address when accessing the cache into tag, index and block offset. In this case, we see that the index bits are part of the page offset. The page offset does not change during address translation. So in this case, we can index the cache using the virtual index because it is the same as the physical index, and later when we have to do the tag comparison, we can do so using the physical tag. When are the cache index bits part of the page offset? Well, this is the case when the page size is larger than or equal to the number of sets times the block size. Is this common? Well, let's look at an example. A typical page size is 4 or 8 kilobyte. And the core duo instruction cache had the following parameters: size 32 kilobyte, associativity 2, and a block size of 64 bytes. In this case, the number of sets times the block size, which equals the cache size divided by the associativity or number of ways, equals 16 kilobyte. So the answer is almost, but not completely. If the page size is 4 kilobyte, then the index and the page number have 2 bits in common, and when the page size is 8 kilobyte, they have 1 bit in common. What could be done about this? 2 solutions immediately come to mind. The first is to increase the associativity. Then the index shrinks and may correspond completely to the page offset bits. Unfortunately, as we saw before, increasing the associativity may also increase the hit time. The second option is to restrict a little bit the virtual to physical page mapping. Then also the virtual address and the physical address will have more bits in common. This technique is called page coloring, and I will describe it on the next slide. Let me give an example of page coloring. Suppose a page is twice the size of the number of sets times the block size. Then the index and the page number have 1 bit in common. In other words, only 1 bit of the index is translated during address translation. Now, page coloring restricts the mapping of virtual pages to physical pages such that virtual page numbers that end in a 0 map to physical pages that end in a 0, and virtual pages that end in 1 map to physical pages that end in 1. Here's an example. The virtual page number ends in a 1. Then it may only map to a physical page whose number also ends in 0, as shown here. This in turn implies that the cache index has to start with a 0 and is available before the TLB is accessed. So the cache can be accessed using the physical index. Another way to avoid address translation during cache indexing is to employ virtually indexed caches. This figure here on the left shows again the conventional organization. The cache is physically indexed and physically tagged as assumed before. This figure, on the other hand, shows a virtually addressed cache. In this case, the index as well as the tag are taken from the virtual address. So the CPU generates a virtual address, and that is used to index the cache as well as for the tag comparison, and only when there is a miss in the level 1 cache, the virtual address is translated to a physical address using the TLB, and the physical address is sent to memory. The third possibility, illustrated here, is to use the virtual index and the physical tag. This allows the cache access to begin immediately with the virtual index. At the same time, the TLB is accessed to get the physical address. When the physical address is available, its tag part is used for the tag comparison. Virtually addressed caches have a number of problems, however. The first is that page level protection is checked during virtual address to physical address translation and must be enforced no matter what. A solution to this problem is to include the protection information in the cache and to copy it from the TLB to the cache on a cache miss. The second problem of virtually addressed caches is that every time a process is switched, the virtual addresses refer to different physical addresses. One solution to this problem would be to flush the cache on every process or context switch. But obviously, this increases the miss rate. Another solution is to add the process identifier PID to the cache tags. Then there is a hit only when the tags match, as well as the process identifiers. The biggest problem of virtually addressed caches is, however, the synonym or alias problem. Operating systems and user programs may use two different virtual addresses for the same physical address. These duplicate addresses could result in two copies of the same data in a virtually addressed cache. So if one of them is modified, the other one will have the wrong value. There are hardware solutions to the synonym problem that guarantee that the same data cannot be cached twice, but I will not discuss them. Finally, an exercise that asks you to explain what a virtually addressed cache is, its advantages and its problems, as well as a solution to one of these problems. We just discussed virtual address caches, so there is no need to answer these questions. The real challenge is, however, will you be able to transfer these questions in a couple of weeks or months from now? This concludes this lesson. Thanks for watching. In the next lesson, I will describe several techniques to reduce the cache hit time. Stay tuned.